Hi everyone, my name is Vikas Ahmed. I am from Department of Computer Science, Otago University, New Zealand. Today I am going to present for IEEE ICC 2020, and then the topic of my research is full digital transmit beamforming with low RF complexity for large-scale millimeter wave MIMO system. The motivation of my work is for future wireless communication system. It is expected to have large number of antennas to achieve beamforming gain, and digital beamforming is considered optimal due to accurate beam steering, generate multiple closely spaced beam, and eliminate interference by setting nulls towards the interference. The recent study in reference to showed that the digital beamforming is the only solution for the successful realization of 5G millimeter wave networks, and the optimality of digital beamforming comes from the fact that it has the ability to perform uh, independent preservation for each antenna signal from baseband until antenna aperture. But the problem with full RF complexity digital beamforming is that it requires one separate RF chain per antenna. It makes the hardware extremely bulky and complex and expensive and power consuming. So the important question arises here that is the low RF complexity solution is possible? The answer is yes. There are three different type of solutions. The first is multi-tone modulation scheme in which the analog signal is modulated by using FTM modulator, and the modulated signal is summed up and processed by a common RF chain. And before the antenna, each antenna signal is independently recovered by using FTM demodulator. The problem of this scheme is that it requires separate local oscillator for modulation and demodulation, and for large-scale antenna arrays, a large number of local oscillators causes uh, the phase noise in the system, which significantly impact the system performance, and the circuit also becomes expensive as well. So the second scheme is time sequence phase weighting, in which the digital baseband signal is weighted by using inverse Wash-Hadamard transformation matrix, and the signal of each antenna is recovered by using analog phase shifter network, in which analog phase shifters are arranged in such a way that they act as a Wash-Hadamard matrix. The problem with this scheme is that for large-scale antenna arrays, it requires a very complex phase shifting network, and the limited resolution of analog phase shifters also degrades the system performance. So the third scheme is special multiplexing of local element. In this scheme, the digital baseband signal is multiplexed by using time-domain multiplexing, and it this scheme uses only one digital to analog converter and one local oscillator. So the multiplex signal is recovered by using analog switches in analog domain. According to Nyquist sampling theory, when we sample a signal, the sampling rate should be number of antenna times the bandwidth in order to recover the signal properly. But the SMILE works very well for a small antenna array. However, its implementation for large antenna array creates bottleneck due to sampling frequency. So in this work, we have solved this sampling speed problem by dividing a large antenna array into smaller groups, and each antenna group is processed by one common RF chain. So in this way, we can reduce antenna switching speed significantly. And we have designed our proposed scheme in such a way that each antenna group performs beamforming, whereas the special multiplexing exists among the antenna groups. So we formulate our problem by this example, that consider we have two antenna groups which have channel matrix H1 and H2. So we intend to make this H1 and H2 maximum orthogonal with each other, whereas H1 and H2, H1 elements of H1 should form a close to rank 1 channel matrix with the receiver antenna, and similarly for H2. So we define the maximum the capacity problem as equal power allocation problem, in which we divide SNR by the number of transmit antenna, and the number of antenna in a group are cannot be greater than n maximum, and this n maximum is derived from the available switching speed of the system. It can be noted that for optimal grouping, the problem becomes NP hard, because for large antenna array, the possible combination becomes very huge. So we have solved this problem by using a greedy selection approach. Uh, and for that, we have taken the assumption that the perfect channel state information is available at transmitter and receiver. And according to reference 1, the millimeter wave transmission is expected to be in line of sight, so TDD mode can be used. And we have evaluated for narrowband system and considered ideal hardware. In the first step, we select the first element of each antenna group in such a way that they should be as much orthogonal as possible for the given snapshot. And for that purpose, we have used the greedy uh, algorithm, which is strong rank revealing RRQR. And in this algorithm, we divide the channel in two parts, HS and HB in the first step. So we define the volume of a matrix HS as determinant of HS harmonition, which is equal to the product of square of singular values of HS. So according to Poincare separation theorem, the singular values of a subset of a matrix should always be less than or equal to the singular values of full channel matrix. So uh, our intention is that increase use the HS in such a way that the singular values of HS should be very close to H. So for that, we have used the Grant-Schmidt orthogonalization based QR decomposition and defined a permutation matrix phi. But the studies shows that QR decomposition has uh, poor numerical accuracy, and due to this poor numerical accuracy, the selected columns start to lose the orthogonality. So for that, we have defined one criteria which is given in equation 1, in which we want to increase the volume of channel matrix A, which is the subpart, and when we will increase the volume of matrix A, it will increase the volume of channel matrix HS, and increasing the volume of HS will contribute to increase the channel capacity. So in this criteria, rather than performing the actual permutation or swapping of the column, this criteria checks that if the ith column and jth columns are swapped, then what will be the value of determinant of A bar over determinant of A? If it is greater than 1, then the swapping should be performed. Otherwise, the maximum volume is already accumulated in the channel matrix A. So in the step 2, uh, we want to form the close to rank 1 channel matrix for each antenna group, and when we form this close to rank 1 channel matrix, for that we have defined a criteria which is we named as eta, and it is the ratio of largest singular value to the all singular values, and when eta becomes very close to 1, the channel the rank of the channel for that group becomes also very close to the 1. And in order to uh, in order to make the groups, we have defined two conditions: that the current number of antenna elements in a group should not exceed the maximum limit, and then the similarity index eta should be maximum at that given pair. So in this way, we merge the selected column and the selected groups and remove that column from HB. By using this iterative procedure, we merge all the columns of HB to HS, and in this way, we form the antenna groups. So based upon this algorithm, we have simulated our system, and we can consider the example of a 16 RF chain. For example, in case of digital beamforming, we need 64 RF chain, but for our solution, we need only 16 RF chain. This can save 75% RF complexity. But the cost of this saving is the extra 16 analog switches with a switching speed of 4B. So by using our proposed scheme, the loss in channel capacity for 5 dB SNR is 4.3, and similarly for SNR 20 it is 8.10%. The important point to note here is that when we increase the number of RF chains, the channel capacity start to become equal to full RF complexity digital beamforming, and at the same time, if we reduce the RF complexity, the number of the antenna switching speed requirement also start to increase. And then the reason for loss in capacity is also that when we form close to rank 1 channel matrix and the number of antennas are increased in the group, so if they are not exactly close to rank 1, the antenna will start to interfere with each other, and then it will degrade the channel capacity as well. So overall, in this paper, we have proposed a lower of complexity digital beamforming, and the extra we have reduced the RF complexity, and the cost of this reduction in complexity is that extra analog switches, but we can note that which the extra analog switches are much cheaper as compared to digital to analog converters. And at the same time, we have achieved a comparable channel capacity with full RF complexity digital beamforming. And due to reduced hardware complexity, we expect that we have less number of local oscillators, so our system is expected to be more robust for the phase noise. So the constraint in this design are that the energy efficiency can be improved by using low resolution digital to analog converters, and since we have evaluated our system for ideal hardware, so we are interested to evaluate our system in our future work for realistic hardware to see the performance of our proposed system. So that's all from my side today. And if you have any query, I will be more than happy to answer it, and it will help me to increase my knowledge as well. So please contact me at wahmad@cs.otago.ac.nz. So that's all from my side. Thanks a lot for your patience.